Lesson 6.2, Multiplying Polynomials. How do you multiply polynomials, and what type of expression is the result? Probably the best way to multiply polynomials is with the distributive property. And your result will be another polynomial. Analyzing a visual model for polynomial multiplication. The volume of a rectangular prism is the product of the length, the width, and the height of that prism. If the dimensions are well known, then the volume is a simple calculation. What if some of the dimensions are given as binomials? A binomial is a polynomial with two terms. Binomial, right here. A polynomial with two terms, like x plus 3 is a binomial. 2x minus 7 is a binomial. How would you find the volume of a rectangular prism that is x plus 3 units long, x plus 2 units wide, and x units high? The images below show two methods for finding the solutions. Take a second and look at those. If you need to, stop the video. The first model shows the rectangular prism, and its volume is calculated directly as a product of two binomials and a monomial. So like x times x plus 2 times x plus 3. It's shown up here. The second image divides the rectangular prism into four smaller prisms, each dimensions of which are each they're monomials, like x and 3 and 2 and whatnot. The volume of a cube v sub 1, where all the sides have a length x, is, well, x times x times x. That would give you x cubed. The volume of a rectangular prism v sub 2 with dimensions x by 2 would give you, well, that's x times 2, which is 2x squared. Now we'll put those back up in there. Let's see. X times x times x is x cubed, and that was x times 2, which is 2x squared. The volume of a rectangular prism v sub 3 with dimensions x by 3 is x times 3, which is 3x squared. The volume of a rectangular prism v sub 4 with dimensions x by 3 by 2 would be x times 3 times 2, and that gives you 6x. So the volume of a rectangular prism is the sum of the volumes of the four smaller regions. Volume 1 plus volume 2 plus volume 3 plus volume 4. Volume 1 was x cubed. Volume 2 was 2x squared. Volume 3 was 3x squared. And volume 4 was 6x. Now, if you'll notice, these two here, they're like terms. So we can combine those, and that gives you x cubed plus 5x squared plus 6x. Good deal. If all three dimensions were binomials, how many regions would the rectangular prism been divided into? If all three dimensions were binomials, how many regions would the rectangular prism? Well, think about it. So see if we can't draw that. Try to draw that. So here we've got a cube. All right, we've got a cube, and that goes down like that. And then just combine that, and then of course that's down there like that. We'll just pretend that's a little bit better. What if it says if all three dimensions? So what if, you know, like this one here, we cut like this. All right. So that might be x, and that might be 2, and we cut this one here, this way here, and that was x, and that was 3, and we cut this one here, this way here, and that was x, and that was, we'll say 4. 1, 2, 3, 4, and see those 4. That becomes if you slice it up, that becomes, you're looking at something that goes like this, and then something that goes like that. And see, you know, this line here, this red line here, that extends over like that, over that way there, and this green line here, that was supposed to be green, that green line right there, that's going to extend down like that. All right, and then it extends down there like that. And this blue line extends across there like that and like that. And so how many do we have? We got 1, 2, 3, 4, and then we got 5, 6, 7. We got 8 little cubes. Can this method be applied to finding the volume of other simple solids? Sure, we can break a solid up. Sure, usually you can with simple solids, yes. Are there solids where this process would be difficult to apply to? Yes, most definitely. Not all solids, you know, this is a regular cube. It's pretty easy to break it up. Not all solids are that easy. Are there any solids that this method cannot be applied to? Yeah, let's see. Spheres comes to mind. SP. Spheres. S-P-H-E-R-E. Spheres. You can't do that. It's finding the volume of any object is pretty hard, especially spheres and stuff like that. Multiplying polynomials. Multiplying polynomials involves using the product rule for exponents and the distributive property. The product of two monomials is the product of the coefficients and the sum of the exponents of each variable. Remember, a monomial is, well, this is a monomial, and that's a monomial. So it would be 5 times 6, that gives you 30, and x to the first times x to the third would be x to the 1 plus 3, and you get 30x to the fourth. When multiplying two binomials, the distributive property is used. Each term of one polynomial must be applied by each term of the other. And we've done this before. We call it FOIL. Okay. The first, that's the first. And then outer would be 2 and x. So that's there. Inner would be 3x and 1, or they spun that around. But anyway, 3x and 1, 3x and 1, that's right there. And then last would be 3x. I've already used that color. 3x times x right here. Okay, and we've done that before. A polynomial 2 plus 5x plus 3x squared is called a trinomial because it has 1, 2, 3 terms. 3 terms. Perform the following polynomial multiplication. Okay, find the product by multiplying horizontal. Y'all can follow through that one there, and we'll do B together. So go ahead and stop the video and follow that through, and then when you come back, we'll do B together. Glad you're back. Find the product by multiplying vertically. So we've got negative 7x squared plus x plus 2 multiplied by, so that's multiplied by times 3x minus 4. Negative 4 times 2 gives you negative 8. Negative 4 times x gives you negative 4x. Negative 4 times negative 7x squared would give you 28x squared. Then we have 3x times 2. That's going to give you 6x. 3x times 2. And we're going to see how we keep the x's together? Then you got 3x times x. That's going to be 3x squared. And we'll keep those together. And then 3x times negative 7x squared. That's negative 7 times 3 is negative 21. X squared times x is x to the third. 21x to the third. Now let's start back here, and let's bring that 8 down, and that gives you 8, negative 8. And then we're going to add these two here, negative 4 plus 6. That's going to give you 2x. And then we'll 28x squared plus 3x squared gives you 31x squared. And then we just bring that down. Good. Are there any like terms? No. So therefore, 3x minus 4 times 2 plus x minus 7x squared is negative 21x cubed plus 31x squared plus 2x minus 8. And did I make a mistake here? Nope, it's good. It's good. Now let's do number 3. Your turn. So y'all go ahead and stop the video and you try it. When you come back, we'll do it together. Glad you're back. First, I like to rewrite them in descending order. So I'm going to rewrite this as 2x plus 3 times 5x squared minus 7x plus 4. Okay. Now doing that, first I'm going to distribute this 2x inside the parentheses. There. First I'm going to distribute that. And so I've got 2x times 5x squared plus and 2x times negative 7x plus 2x times 4. Next, I'm going to distribute this 3 in there. So I got plus 3 times 5x squared. That's 3 times 5x squared. Plus 3 times negative 7x. So 3 times negative 7x is right there. Plus 3 times 4. And that's the third. Now that I've done the distributing, I'm going to do the arithmetic here. 2 times 5 is 10. X times x squared is x to the third. 2 times 7 is negative 7 is negative 14. X times x is x squared. 2 times 4 is 8. And then x times 1 is just x. 3 times 5 would be 15. x squared. 3 times negative 7x would be negative 21x. And then 3 times 4 would be 12. Now I'm going to look. X cubed. Do I have any other x cubes? Nope. So I've got 10x cubed. Now x squares. Let's see if we got any x squared. I got negative 14x squared and plus 15x squared. Well, negative 14 plus 15 is positive 1. So I've got plus x squared. Then we have 8x here. Do I have any other x? Minus 21x. Minus 21. So that's going to give me negative 13x. And what do I have? I just have 12 left. So I have 12 left. So we'll just add 12 there. And voila, you're done. Let's take a look at this next one. Here again, I think the first thing I want to do is rewrite it. X minus 6. Put my exponents in descending term. Negative 4x squared minus 8x plus 3. All right. Let's distribute the x. X times, so we got x times negative 4x squared plus, and then x times negative 8x, x times negative 8x, and x times 3. All right, now let's do this negative 6. So I got minus 6 times negative 4x squared, and then negative 6 times negative 8x, so it should have been minus 6 times negative 8x, and then the last one, I'm out of colors. Let's just use this green one again. Negative 6 times 3 minus 6 times 3. All right. Now we need to do the arithmetic. X times negative 4x squared would be negative 4x cubed. And then you have x times negative 8x would be negative 8x squared. X times 3 is 3x. Negative 6 times negative 4, that would be plus 24x squared. Negative 6 times negative 8 would be plus 48x. And then negative 6 times 3 would be minus 18. So let's see. Let's start off here. Negative 4x cubed, or any other x? Nope. So we got negative 4x cubed. And then you got negative 8x. You got plus 24x. That's going to give me plus 16x squared. I said x, I mean x squared. Negative 8x squared plus 24x squared gives you positive 16x squared. We have 3x here. Do we have any? Oh, we got, so 3x plus 48x would be plus 51x. And then I just had the negative 18 left over. And there you go. You have multiplied a binomial to a trinomial. Good job. Modeling with polynomial multiplication. Many real-world situations can be modeled with polynomial functions. Sometimes a situation will arise in which a model is needed that combines two quantities modeled by a polynomial function. In this case, the desired model would be the product of two known models. I'll let y'all read A, and then when you get back, we'll do B together. Glad you're back. Miss Leo runs a small dress company. From 1995 through 2005, the number of dresses she made can be modeled by n of x equals 0.3x squared minus 1.6x plus 14. And the average cost to make each dress can be modeled by C of x equals negative 0.001x squared minus 0.06x plus 8.3, where x is the number of years since 1995. Write a polynomial that can be used to model Miss Leo's total dressmaking cost, T of x, for those years. And it gives you the formula here. T of x equals nx times cx. Multiply the two polynomials. So you've got n of x, which is 0.3x squared minus 1.6x plus 14 times C of x, which is this is your operator here, negative 0.001x squared minus 0.06x plus 8.3. Now we're going to do just like we did before. We're going to take 8.3 here, and we're going to multiply it times 14, and we get 116.2. Then we're going to take 8.3, and we're going to multiply it by negative 1.6, and we get negative 13.28x. Then we're going to take 8.3, and we're going to multiply it by 0.3x squared, and that's going to give us 2.49x squared. Good, we've done that one. Now let me get these lines out of the way so you can see what I'm doing with this next one. All right. So we're going to take negative 0.06x, and we're going to multiply it by 14, and we get negative 0.84x. Then we're going to take negative 0.06x and multiply it by negative 1.6x, and we're going to get plus 0.096x squared. And then we're going to multiply, use a different color here, negative 0.06x times 0.3x squared, and we're going to get negative 0.018x cubed. Okay, again, let me move these lines here so we don't get confused. And all right, the last one. Now remember, this is a trinomial times a trinomial. The last one, we've got negative 0.001x squared times 14, and that's going to give us negative 0.014x squared. So we just moved the decimal places over too. All right. Next, we have negative 0.001x squared times negative 1.6x, and that's going to give us 0.0016x to the third. And our last term, negative 0.001x squared times 0.3x squared will give us negative 0.0003x squared. All right, good. Let me clear these out so there's no confusion. Get rid of these. All right. Now we're going to start off by bringing it down. You got this right here. Bring it down. There's no other constants. Second, we're going to add these two here, and we're going to get negative minus 14.12x. Next, we'll add these three items together and bring that answer down here, and that's going to give us 2.572x squared. We'll add these two here together and bring that answer down, negative 0.016x to the fourth. And I put a square here, and I know that's supposed to be to the fourth power. X squared times x squared is x to the fourth. I don't know why I did that, so that's a 4 right there. Oops. All right, therefore, the total dressmaking cost can be modeled by the following polynomial, where x is the number of years since 1995. So you got negative 0.0003x to the fourth minus 0.0164x cubed plus 2.572, and that's a 2, x squared minus 14.12x plus 116.2. All right, good deal. My turn, or our turn. Take a minute, read that, see what you can do with it. When you get back, we'll do it together. Glad you're back. Britt runs a small toy store specializing in wooden toys. From 2000 through 2012, the number of toys Brent made can be modeled by n of x equals 0.7x squared minus 2x plus 23. And the average cost to make each toy can be modeled by c of x equals negative 0.004x squared minus 0.08x plus 25, where x is the number of years since 2000. Write a polynomial that can be used to model Brent's total cost for making the toys, t of x for those years. So again, t of x will equal n of x times c of x. All right. So we're going to have 0.7x squared, 0.7x squared minus 2x plus 23 times negative 0.004x squared minus, and I'm going to put a 0, so 0.8x plus 25. So we're gonna multiply those two, and we'll do like we did in number 4. We've got 0.7x squared minus 2x plus 23, and then I probably might be negative 0.004x squared minus 0.08x plus 25. And I'm going to go and I'm going to move these over. So that's going to be minus, is that 2x? 7x squared minus 2x, and then plus 23. And I'm just doing that so I can keep them above each other. Notice how the constant's here, the x is here, the x squared is there. All right, good. So what do we got here? We've got 25 times 23, and that's going to give us 575. 575. All right. Now we've got 25 times 2, negative 2x. That's going to be minus 50x. Minus 50x. That's plus 75 because those two were positive. Now next we have 25 times 0.7 x squared, and that's going to give us 17.5 x squared. Now for the next one, we're going to have, can I clean that up a little bit? Yeah, I can clean that up a little bit. And then I'll fix that too. All right. The next row, we've got negative 0.8 times 23, negative 0.08x times 23, and that's going to give us 1.84x. 1.84x. And then we're going to multiply these two here together. Negative, negative, that's going to give us a positive. So we're going to have a positive 0.08 x times 2x, and that's going to give us 0.16 x squared. And then we're going to do 0.08 x times 0.7 x squared, and that's going to give us negative 0.056 x cubed. All right, so far so good. The last one, we've got, let's see, we'll do red here. We've got negative 0.004 x squared times 23, and that's going to be negative 0.092 x squared. Now, next we've got negative 0.004 x squared times negative 2x. So we're going to have positive 0.008 x cubed. Do I have a mistake there? 0.08. Oh, I'm doing this in here. So 0.008 x cubed. All right, good. And then the last one. And you got negative and a positive, so you're going to have negative 0.004 times 0.7. It's going to be 0.0028, and x squared times x squared is x to the fourth. All right, we're 3/4 of the way done here. Now see, remember we multiplied those. So let's bring the 575 down. That's our constant. And then these two here, negative 50 plus 1.84x, that's going to give us negative 51.84. That was a negative, wasn't it? Yeah, that was a negative. I should have put the negative 51.84x. That's a positive. And next we do these three here. You got 17.5 plus 0.16 minus 0.092. And let's see. That's going to be 17.568. 17.568 x squared. And that's a positive. Negative 0.056 x cubed plus 0.008 x to the third is going to be negative 0.048 x to the third. And then just bring this down. You got negative 0.0028 x to the fourth. So what does that give you? T of x equals negative 0.0028 x to the fourth minus 0.048 x cubed plus 17.568 x squared minus 51.84 x plus 575. So the total cost to bake toys from 1990, what was it, 1990 to, or from since 2000 would be T of x equals, and there you go. Verifying polynomial identities. You have already seen certain special relationships. For example, a difference of two squares can be easily factored. X squared minus a squared equals x plus a times x minus a. This equation is an example of a polynomial identity, a mathematical relationship equating one polynomial quantity to another. Another example of a polynomial identity is x plus a squared minus x minus a squared, which is 4ax. The identity can be verified by simplifying one side of the equation to match the other. All right, I'll let y'all read A, and let's go down here to B. When you get back, we'll do B together. So we have a plus b times a squared minus ab plus b squared equals a cubed plus b cubed. The right side, this side over here, is already simplified. So we're going to have to simplify the left side to make sure that it works. So we're going to distribute a. So a times a squared is here. And then we have a times negative AB, and then we have a times b squared, right there. Now that we've done those, let's do the bottom half, or the b's. B times a squared right there, and then we have b times negative AB right there. I'll try to get a different color for that. B times AB, B times negative AB. And then the last one would be B times B squared. And there we go. All right, let's do the arithmetic. A times A squared is A to the third. A times AB would be A squared B. A times B squared would be AB squared. B times A squared is A squared B, A squared B. B times negative AB would be negative AB squared, and then B times B squared would be B to the third. Okay. Let's rearrange the terms and put stuff together. So you got A cubed minus A squared B. All right. That was supposed to be A squared B, and then plus A squared B. So we move that term there. And then you have AB squared minus AB squared right there, plus B squared. Now, we did that so that we can combine like terms. Okay? Because this negative AB plus negative A squared B plus A squared B, those cancel out. And then AB squared minus AB squared, those cancel out. And you're left with A squared plus B squared, or A to the third plus B to the third. So that gives you A cubed plus B cubed. Therefore, the statement A plus B times A squared minus AB plus B squared equals A cubed plus B cubed is a true statement. It is a true statement. Number six, your turn. show that a to the fifth minus b to the fifth equals a minus b times a to the fourth plus a cubed b plus a squared b squared plus ab to the third plus b to the fourth. So we're going to show. Now, if you'll notice this time, the left side is fully simplified. We just got to do the multiplication here and then simplify. So we got a times a to the fourth, and I'm just distributing the a in there, and then a times plus a times a cubed b plus a times a squared b squared plus a times a b to the third. It's supposed to be an a. And then a times b to the fourth. Yeah, guess what? Now we're going to do the minus b in there. So minus b times, well, it's a to the fourth minus b, and I'm doing it to each one, a to the fourth, then minus b times a cubed b minus b times a squared b squared, a squared b squared, and then minus b times a b to the third, and then minus b times b to the fourth, minus b times b to the fourth. All right, let's do the arithmetic. Now this is really shortened up here when we do this arithmetic. Equals a times a to the fourth is a to the fifth, plus a times a to the third b would be a to the fourth b, plus a times a squared b squared would be a to the third b to the third, and then a times, that's going to be plus a squared b to the third, plus, and then a times b to the fourth would be a b to the fourth, minus, and then you got b times a to the fourth would be a to the fourth b, and then b times, that's going to be minus b times a to the third b would be a to the third b squared, minus b times a squared b squared would be minus a squared b to the third, and b times ab to the third would be minus a times b to the fourth, and then b times b to the fourth would be minus b to the fifth. Now let's look and see if we have any like terms. All right, we have a to the fifth. Do we have any more a to the fifth? No. So we have a to the fifth, a to the fourth b, a to the fourth b, and then do we have any more a to the fourth b? A to the fourth b right there. So those two cancel out. Good deal. We have a cubed b cubed. We have any more? Is that, let's see, that's the third term. 1, 2, 3. A cubed, that's supposed to be b squared. B squared. Poor penmanship. B squared. So we got a cubed b squared minus right there. So those two cancel out. Good deal. And let's see here. A squared b to the third. And we got minus a. So those two will cancel out. Good, good, good. And let's see here. Let's try this green here. We got ab to the fourth minus ab. So those two will cancel out. And what are we left with? What's left? Minus b to the fifth. Well, that's what we had. A to the fifth minus b to the fifth equals a to the fifth minus b to the fifth. Good job. What about 7? What about 7? Let's try 7. If you want to, you can stop the video and try it on your own, and then come back and follow along. See how well you did. If you notice, the right side is already simplified, so we just got to simplify the left side. So you got a times a squared plus a times ab plus a times b squared. And then minus b times a squared minus b times ab minus b times b squared. This one seems a whole lot simpler after that last one, doesn't it? Let's look and see what we got here. We got to do the arithmetic. A times a squared is a to the third, plus a times ab would be a squared b, plus a times b squared would be a b squared, minus b times a squared would be a squared b, minus b times ab would be minus ab squared, and minus b times b squared minus b to the third. Remember, that was supposed to equal a cubed minus b cubed. And we don't really know yet, so let's put a question mark there and there. All right, let's simplify. We got a to the third. Good. A to the third. No other a to the thirds over here? Good, 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 good. All right, we have a squared b right here. A squared b. And, oh, we got minus a. So those two cancel out. Good, good. And we got ab squared minus a. So those two cancel out. Good, good, good. And it seems that all we got left is minus b cubed. And I would say that a cubed minus b cubed equals a cubed minus b cubed. Not a problem. Good deal. Using polynomial identities. The most obvious use for polynomial identities is simplifying algebraic expressions, but polynomial identities often turn out to have non-intuitive uses as well. So I'll let you read example 4a, and then we'll come down and we'll do 4b together. The identity x plus y squared equals x squared plus 2xy plus y squared can be used for mental math calculations to quickly square numbers. Find the square of 27. Well, we're going to let x equal 20 and y equal 7. We're going to let x equal 20 and y equal 7. So we're going to have 20 plus 7 squared. All right. And then 20 squared plus, and then we got 2 times 20 times 7 plus 7 squared. All right. 20 squared is 400. 2 times 20 is 40. 40 times 7 is 280. And then plus 49. So that's 680 plus 49. I get 729. All right. Verify by using the calculator. So let's try that. And we need to go to calculate. 27 squared, 729. Wow. So if you're stranded on a beach in Aruba and someone asks you to square 27, you now know a method to square 27. Your turn. The identity x plus y times x minus y equals x squared minus y squared can be used for mental math calculations to quickly multiply two numbers in specific situations. Find the product of 37 and 43. So, hint, what values should you choose for x and y so that the equation calculates to, let's see here, x plus y times x minus y. So let's see, 37 or let's do 43 because that's x plus y. That's going to be 40 plus 3, right? And then that gives you 43, and then 40 minus 3, that gives you 37. So essentially we're multiplying 47 times 30, 43 times 37. And then we'll put, that's going to be 40 squared minus 3 squared, right? All right, so let's do this. 40 times 40, that's going to be 1,600, right? That's first. And then 40 times negative 3 is going to be minus 120. 3 times 140 is going to be plus 120. And then 3 times negative 3 is going to be minus 9. Okay, now 40 squared, that's going to be 1,600 minus 9. 1,600 minus 9. All right, so minus 120 plus, that's going to cancel out, and we end up with 1,600 minus 9. 1,600 minus 9. That's a terrible looking 9. Let's straighten it up a little bit. 1,609, I get 1,591. 1,591. Let's check that with a calculator. That's 43 times 37. So 37 times 43, 1,591. Good deal. That worked. Number 9. The identity x minus y squared equals x squared minus 2xy plus y squared can be used for mental math calculations to quickly square numbers. Find the square of 18. Hint, what value should you choose for x and y so that the equation calculates the square of 18? So let's see, since we got a minus, how about 20 minus 2? Those are nice, easy numbers to use. Squared, 20 equals, and then that's going to be 20 squared minus 2 times 20 times 2, right? And then plus, and then 2 squared. 2 times 2 is 4, so 20 times 20 would be 400 minus 2 times 20, that would be 40, times 2 would be 80 plus 4. So 400 minus 80, that would be 320 plus 4 is 324. So let's try that. 18 squared, 324. 324. It works. Eureka. Elaborate. What property is employed in the process of polynomial multiplication? The big D, distributive property. The big D, distributive property. Big D, big distributive property. How can you use unit analysis to justify multiplying two polynomial models of real-world quantities? How can you use unit analysis to justify multiplying two polynomial models of real-world quantities? The units of the polynomials need to combine in such a way that their product is the desired unit. Give an example of a polynomial identity and how it's useful. X minus y squared, that's one, and that's useful for mental math. Essential question. Essential question, check it. When multiplying polynomials, what type of expression is the product? It's a polynomial. Folks, that concludes lesson 6-2. I hope you have a good evening. Thank you.